Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 13. Student, basically, as we started lecture number 11, in lecture number 11 and lecture number 12, okay. In that lecture, as you see that, in that lecture, basically, we covered the the shear design of a flat slab system. And you see the thorough explanation of that lecture, what we basically covered, what is shear reinforcement and what different kind of arrangement we will provide in case of flat slab system when shear reinforcement basically needed. Although in that lecture we try our best to prevent the shear reinforcement in a flat slab system because it makes your design uneconomical, but as punching shear is a governing criteria in that case, so most of the time it is needed to provide shear reinforcement. So we have different arrangement. We have column capital, drop panels, bent up bars, shear heads, studs, and we did so many examples on it. And I already explained some part of this lecture in my other lectures, as I will already uploaded those lectures to a DDM with the playlist in DDM method. Okay, so these two lectures are basically related with the these two lectures. This lecture number 11 and lecture number 10 is basically devoted to punching shear design. So here I basically explain the integral beam design, why we need punching, why we need to provide shear reinforcement, and what are the cases basically where we have to provide integral beams. So up to this lecture basically, which is up to lecture number 12, okay, we doesn't include the effect of moment transfer, okay, the unbalanced moment transfer. Now, as already in lecture number from lecture number 1 to lecture number 10, using the equivalent frame method, as we did this example, as you people see here, that we start an example and we complete that example in lecture number 9. Okay, in lecture number 10 basically we covered in another example, but this was the example which we covered in lecture number from lecture number 3 to lecture number 9. And here you see when we did our moment equivalent frame analysis, and when we complete our equivalent the moment distribution table, we see here that we got the unbalanced moment directly from the moment distribution table. But this is very important question that and already you see here that these are the unbalanced moment which we basically got from the moment distribution table in the case of equivalent frame method. So this is the advantage of using the equivalent frame method, because it gives you directly the unbalanced moment. These moments which you see here, these are the unbalanced moment. These are called unbalanced moment. Why we call this unbalanced moment, I will explain this in later stage. But the equivalent frame method basically it gives you directly the unbalanced moment. And you see here that then we distributed these equivalent unbalanced moment by the stiffness, by the relative stiffness of the top column and the bottom column, and they are distributed. And I thoroughly explained the distribution, I think so, in lecture number 5 and 6, okay, and how we distribute it and how we draw these moment diagrams. Okay, now this is the beauty of, you can say, the equivalent frame method. But when we want to analyze such a beam system, such a slab system, by using a direct design method, so how we got these unbalanced moment? This is a very important question. One of the most important question that I want to share, that you see at the interior column there is insignificant amount of unbalanced moment, as you see here. but the effect is dominant on the exterior column. Okay, it is very important. And basically these movements is due to the lateral vertical loading, the vertical or you can say the gravity loading. Okay, dead loads and live loads. Sometimes we have lateral loads. Okay, lateral loads may be a wind load, maybe an earthquake load. They basically causes very huge unbalanced moment. Okay, and they will be dominant basically on the outer columns, on your edge columns, and there will be lesser amount on the interior columns. But in that case these movements are dominant. Okay, now let me explain what are the different cases due to which govern the unbalanced moment. Okay, let's say we have this frame system. Okay, and let me share you some diagrams. Okay, not this one, this one. We did this example, and as you see in this example, this is 25 feet and this is 20 feet. So all the spans in x direction are in east-west direction is 25 feet, 25 feet. So the adjacent spans are equal. So in this case there is a little bit unbalanced moment. Although remember, the unbalanced movement should be caused by the live load. It should be remembered, not by the dead load. And there will be, you can say, zero or a very little amount of unbalanced movement due to the difference in geometry. Okay, because let's say if this is 25 feet and this is not 25 feet, let's say this is 15 feet, this is 18 feet. So due to the difference in geometry, okay, there will be some kind of unbalanced moment. Similarly, due to the pattern loading of live load, okay, as I already explained this in my lecture number 7. Okay, for example, if there is, let's say there is live load, so due to this live load, and already there are no live loads, so due to this live load, as you already know that due to this live load there is a fixed end moment, okay, or unbalanced moment, and that unbalanced moment is supported by this column, by this interior column. Similarly, this unbalanced moment should be supported by this exterior column. So this is very important. Similarly, if this live load comes here, so it will cause unbalanced moment at this column and in this column. Okay, so once you run the analysis in equivalent frame method, you see the unbalanced moment in at the different locations of each columns. So due to pattern loading, okay, by, you can say, by shuffling the live load from one span to another span, so it will cause unbalanced movement. Similarly, making any kind of changes in the grids of the system, like you see here in this diagram. In this diagram you see this is round about 18 feet, this is 20 feet. So there is, you can say, although the spans are unequal, so it will cause some kind of unbalanced movement, but they will be insignificant because the difference is small. Okay, but if you look to this diagram, you see here this span is, and this span, or you can say they are the adjacent span in this zone, like in grid A, B and C, they are nearly same, but here you see 5.8, 6.7. so due to this changes in the grids, it will causes the unbalanced movements at this column, at this column. Okay, similarly in the y direction you see this is 8 feet, this is round about 6 meter, and this is 8 meter. So you see the change, so that's why it will also causes the unbalanced movement at this column, at this column. So it is important that you have to understand the geometry of the system, and because the unsymmetrical geometry also causes unbalanced moment. okay. And similarly, by placing the shuffling the live load pattern, it will also causes unbalanced moment. And similarly, due to lateral loading, there will also unbalanced moment. Remember, you have to run the analysis for lateral loading, similarly for the live load patterns, okay, which we already explained it in my from lecture number 3 to lecture number 9 in equivalent frame method, and you see their effect, that how they causes the unbalanced moment. And similar due to geometry, okay, you see the movement. So in the final stage, when you are going to design your any column, you have to sum up these movements, because some movement cancel out each effect. Okay, let me discuss it. Here you see, for example, you calculate the movement right here due to lateral loading. Let's say its direction is in this way, okay, and you calculate the unbalanced moment due to live load, it will be in this way, okay. Similarly here, let's say you find out the direction, okay, and it will be in this way, okay. So for each case you find out, for each span you find out the direction of the movement, and finally you have to extract this joint, okay, right here, and you have to show all those movements, okay, which is acting over that joint, and you have to find out the net movement over this joint, okay, because some movement will cancel out each effect. Like you see here, this one, let's say this is 10 kf feet movement, and this is, let's say, 9 kf feet movement, so the net effect will be anti-clockwise due to this movement, okay. And you see this one, let's say this is 2 kf feet movement, so this one and this one will be added up because the direction is same. So this will be 11, and 11 minus 10, it will give you 1 kf. So as this clockwise movement is dominant, so the net movement will be clockwise, and the direction will be 1 kf feet, okay. So this is the way that how we basically find out the net movements. This is the whole calculation, and you will see inshallah the thorough explanation of these steps. This is just, I want to give you some intro about the topic. Now let's see, we will start the procedure, the lecture. So here you see at the exterior column. Now basically I am explaining the procedure for the direct design method, because in equivalent frame method you got the movement, the unbalanced movement, directly from the moment distribution table, and already you see this in lecture number 6-7, okay, that how we basically get those movement. But already some student asked this question, that how we can basically, because in direct design method, if we have a flat slab system or flat plat slab system, so there is a column slab joint. So how the movement transfer from a slab to a column, okay, there are cases. ACI code basically explains the procedure for exterior column as well as for the interior column. In the case of the exterior column, you see here ACI code, this section, this clearly specify. Let me show you this section. This is 13.6. now here you see section 13, and in section 13 you see 13.6. this section you can see here the gravity load moment. Remember, the gravity, not the lateral load, to be transferred between slab and each column, it should be remembered, in accordance with this section shall be 0.3 m0. This is very important. And what is m0? You already see this in DDM method, okay. m0 is QUL2N squared divided by 8. This means that 30% of this moment will go toward the H column or the exterior column, okay. This is very important. This is very, very important. Now what does it mean, this 30%? You will see in numerical, but this is very important. Although not specifically stated in the ACI code, this movement can be assumed to be acting at the centroid of the shear parameter. We will cover this portion inshallah in next lectures, that what this sentence means. Okay, you will see what is the centroid, or what is the centroid of the shear parameter. At this stage I am leaving this sentence. The exterior negative moment from the direct design method calculation is divided between the columns above, and this is very important. That's that once you got the moment, the unbalanced moment at this joint, because this is the exterior column, and ACI code says that if you calculate the M naught for this span, M naught, ACI code says that this unbalanced moment at this joint, it will be 0.3 times, let's say this is 30% of M naught. Okay, 30% movement of this will transfer to this column. Now this is the total unbalanced moment, okay, at this joint. Now this moment will be distributed to the top column, okay, and to the bottom column in view of the stiffnesses of these columns. And as I already explained this, okay, here these are the stiffnesses. You got these 45, 35 by just finding by using that 30% of M naught. Once you got this, let's say this is 45, then you have to distribute that 45 in view of the stiffness. Okay, this is the distribution factor, okay, which is got, you see here, distribution factor. Now this will be the next procedure. Okay, once you got the unbalanced moment in direct design method, remember, when you have a flat slab system, it should be remembered. Now in the case of the interior column, it is also important that ACI code also explain this, that if you have an interior column, so what amount of the moment should be transferred to the joint, okay, from the slab to the column. This is very important. At interior column, the moment transfer calculation and the total moment used in the design of the column above and below the floor are also unbalanced moment resulting from an uneven distribution of live load. Okay, this is only, remember, that is the uneven distribution of live load. Okay, it will not explaining due to lateral loading or due to unsymmetrical geometry. It should be remembered. The unbalanced moment is computed by using that the longer span adjacent to the column is loaded with the factored dead load and half the factored live load. This sentence is very important, while the shorter span carries only the factored dead load. The equation is simple and you must understand what does it mean. You see here we have two adjacent spans. This is span 2 and this is span 1, as you see here in this case. Clear? Let's say we have this span AB and span BC. Okay, now these are two adjacent spans. The code says that this AB span should be loaded with the factored dead load, plus you have to apply the factored live load, but that factored live load should be halved. Okay, it should be multiplied by 0.5. okay, half live load, and this BC span, which is the adjacent span, it should be loaded with the factored dead load only. This is important. Okay, this is important. This is the code recommendation. You see here, remember, this one should be the longer span, okay, and this one should be the shorter span if AB differ from BC. Okay, but at the same time, if AB differ from BC, it must satisfy the direct design method limitation. Okay, now you see here span 1 is more than span 2, so span 1 is loaded with the full factored dead load plus half of the live load, and it should be multiplied by the lateral span, okay, that is L2. Now here you see this is the shorter span and it is loaded with the full factored dead load. Okay, now remember the shorter span is denoted by dash line. Okay, it should be remembered. Now coming back to this equation, You see that in the case of a direct design method, when you have a flat slab system, so the coefficient, the lateral distribution coefficient for the moment at this interior face and at this interior face is 0.65. okay, this is 0.65, and for the mid this is 0.35. now this is 0.65 which you people see here, right? This one is that coefficient. Now this is the span, okay, which we already discussed it. And similarly, this is the total moment. This is the total moment at that span. Clear? This is the total moment at this span. M naught. You can say this is M naught. Now, and this one is basically M naught, but this moment is on the shorter span. This dash means is the shorter span. Okay, and I already explained this. Now, once you common this add from this equation and you divide this, you got 0.07. This is the total equation. Okay, now I think so many of the students will see this formula, but I see many students that are unable to use this equation. So you see inshallah how to use this equation. This moment is used to compute the shear stress due to movement transparent in interior column. Okay, and inshallah in my next lecture you will see how what this sentence means, how we can find the eccentric shear by using this equation. Okay, this is very important. Now the simplified form of this equation is this one. This is the simplified form. Okay, and if the spans are equal, like in the case of this, let's say in this case, as you see the adjacent spans in east-west direction and the north-south direction are same, so it will reduce your whole work. The equation is, you can say, adopt a new shape, and this will be the final equation. Now if span 2 and span 1 are equal, okay, adjacent spans are equal. Now we did one example over this example, how unbalanced moment is distributed to the column, to the exterior column and to the interior column. This is an example. We see this example right here, that in north-south direction we have 5 span 12 feet center to center, and at the east-west direction we have 5 spans at the rate of 15 feet center to center. Okay, now this equation, this slab system is divided into the equivalent rigid frame in the east-west direction. This is our interior frame, so this is frame A, and this is the exterior, which is the frame B. And in the north-south direction we have an interior frame, this is frame C, and we have exterior frame, this is frame D. Okay, now you see here that the live load is 72 psf over this slab system, and we have no edge beam and as well as no center beam. The FC frame is this one, FY is this one, service live load is this one, story height is 9 feet. Okay, now we have no edge beam, the column size is 10 by 12 inch. Okay, now calculate the loading as by usual calculation. You already know this. This is the dead load 69 psf, and this is the total factor load, this is 198 psf. Okay, now we find out the M naught, and ln you already know how to find out the clear distance. I already explained this in the lectures, so I don't explain this. Okay, now this is the equation. Okay, that this is the unfactored factored moment, factored load times this is the L2 distance, okay, which is the cross transverse span, and this is the ln, because in this direction if we are analyzing this beam in, let's say, this interior frame, so the clear span will be 15 minus half of this column and half of this column, so we got 58.2 feet cap in the long direction. And similarly in the short direction, the only thing is the which is changed is the L2, and here L2 is 15, because now you see here this is the total width. This is, in this case, this is 15 feet, and span length is in this direction now, 12 minus the size, half size of that and column and half size of that column. Okay, so we got 46.3 fit give okay in the short direction or in the north side direction, and this is the east west direction. Clear? Now not movement for frame A. Okay, all the spans are same, it should be remember. Okay, and we have 58.2 feet. This is for interior equivalent frame and this is for exterior. So for B it considered the half of that moment because exterior frame width is smaller as compared to the interior one, so it considered the 50%, you can say. But you can do this calculation, I already explained this in my these videos. Okay, now similarly for M0C we already calculated, that is 46.3, and for the exterior D rigid frame D we divide this by 2, we got this one. Okay, so these are the final movements, or you can say the total static movement. Now next I just represent the movements for frame A, frame B, frame D and frame C. Okay, how I got these movements, the procedure is simple. If you go to my this channel and you watch these videos thoroughly, you will understand the whole procedure, how we basically distribute these movements for the case of beams and in the case of a flat slab system. So we have different coefficients. Okay, and I thoroughly explained those coefficients in that videos. So the procedure is same. It will be the whole diagrams are explained right in this table. You see we have for frame A we have this M naught, for frame B we have this M naught, and similarly for these two. Now M negative at exterior support. Okay, let me recall it. Okay, because many students don't remember these coefficients. Remember, this is my first or you can say my exterior column. So you already know that at exterior column the longitudinal, we have to longitudinally distribute the moment. It should be remember, we have to first of all we have to longitudinally distribute the moment, and once we longitudinally distribute the moment, then we transversely or laterally distribute the moment. So for longitudinal distribution of the moment, as you see in the equivalent frame method we got directly these longitudinal moments, but in direct design method we have to find these longitudinal moments by using the coefficients. Now this movement, let me discuss it right here. Now because you see here we have a negative movement right here, and what will be its, you can say it's the amount of this moment. The amount of this moment by the ACI code, it says that here it will be 0.26 times of M naught. Okay, and M naught for frame A we already determined. Similarly here it will be a positive moment, remember, it should be remember. Clear? Here we have a positive movement, and the positive movement will be 0, that is 52%. Okay, 52% of M naught. Okay, and similarly here, remember this is the first interior support and this is the exterior face of the first interior support. So here the negative moment coefficient is 75%. Okay, 0.75. Okay, and similarly for this side it is 0.65. okay, and similarly for this positive moment it will be 0.35. okay, so these are the coefficients and I thoroughly explained these coefficients in those videos, so go to those videos and watch those lectures. Now you see the coefficients are already, this is 0.70, sorry, this is my write down is 0.75, but this is 0.70. Now you see all the coefficients, you have to just multiply 0.26 with this 58, you got this value. Similarly this one with this, you got this one, and similarly you have to multiply these coefficients with these moments, you got these moments. Okay, now remember This is the movement, okay, which is, you can say, absorbed by the column strip. In the case of a flat slab system, it must be remembered that a flat slab system, the whole movement at the exterior or the edge column is transferred to the column strip, and zero movement will transfer to the middle strip. It means 100% movement is absorbed by the column strip, while the 0% movement is goes toward the middle strip. Okay, similarly in this case, okay, there is also coefficient that how much of movement, I think so 60% of the positive movement will absorb in the column strip, while the rest of the movement, okay, here try to see here that 60% of this movement will absorb in this portion, while the rest of the 40% will go to the middle strip. Similarly for this one and for this one, for all. Okay, this is 0.70, sorry. Okay, so I explained these coefficients in those lectures. Okay, now what we have to do next, okay, once you got these movements, okay, now the next step is to find out the unbalanced moment at the exterior column, as you see here. Now, as we already discussed it, that the unbalanced moment at the here you see this is 0.3 of the m naught. So m naught is 58, so 30% of m naught will be 17.5 feet cube. Okay, so this is the moment, this is the unbalanced moment which is transferred to the exterior column, this one. Now you have to this 17.5, okay, now it should be distributed to the top column and to the bottom column in view of the distribution factor of this column and that column. Okay, it is important as we did here. Okay, that 45 is multiplied with the distribution factor of the bottom column, and similarly that 45 is multiplied with the distribution factor of the top column, and we got 27. So the same way you have to do the same calculation. Okay, now it is discussed right here that on a flat construction, nearly all 98.8% for frame A and 99.3% for frame C of the exterior frame movement is taken by the column strip. Almost we consider this as 100% movement is taken by the column strip. Already I have this table as well, that from where it basically taken these values. Okay, so you see here that in frame A, frame B, frame C and frame D, you already know these frames and the widths of these okay, of these frames, and the alpha beta factors I already explained this in lecture number, I think so, in lecture number 6.5 of equivalent frame method. So in view of these, okay, you see here the exterior negative movement percent to column strip is 98.8%, and similarly for frame C it is 99.3%. But we mostly consider for the exterior column that for that 900% movement is transferred to the column strip and 0% is transferred to the middle strip. Okay, so this is the procedure basically how we can do the calculation for exterior. Now for the interior we have to use that equation. Okay, so how to use that equation? You see 0.07, we already know this equation, 0.07. now 0.083 is the QDU, and this is 0.058. from where we got this. Okay, now you have to multiply 72 with 1.6 and then divide, you got I think so 115, divide that by 2, you got 0.058, because we have to consider half of the Q dead load. Okay, let me show you that equation. I think so I write this equation. Okay, you see dead load, half of the live load, then we have to multiply L2, and then we have to multiply Ln square. Clear? So okay, here you see in the Nelson book, okay, 0.5 QLU, and we see that, okay, 0.083, 0.05 I already explained it, okay, and 12 is the L2, and Ln is already we discuss it, minus this is the Q dead load, you see here Q du dash, okay, and L2 is 12, Ln is the same one, because the geometry is same. Clear? The geometry is same, and the you can use that short equation as well, because the geometry is same, so you can use this equation, okay, and it will also give you the same results. Clear? Now here you see, okay, and we got 9.5 feet kips for the interior column. This is very important, that remember we have to differently you see find that this moment is 17, while here we have that this is 9.5 feet, okay, 9.5 feet, this one. So this is 9.5 kip feet, okay, which is the unbalanced moment. Now this moment will be distributed to the top column and bottom column in view of the distribution factor, and you see here, as you see here, okay. So this is the distribution factor, and how we can determine it, I thoroughly explained this in lecture number 6, 7, I think so. Now you should remember this point, that you have to start these lectures from lecture number 1. You must have a concept about the direct design method, then start these lectures from lecture number 1. If you watch these videos sequentially, you will understand these lecture, okay. Now we see the calculation for the exterior column for frame A, okay. Similarly for interior column for frame A, this is also for frame A. Now for exterior column, but for frame C, which is the exterior frame in short direction, sorry, in short direction, and you see here, you see this is the, okay, this is the in short direction interiors, okay, this one, this is the interior frame, and similarly this is the interior frame in the long direction, okay. Now okay, so again we will use that 30%, okay, and now remember this is the north south direction, okay, because you have to run the analysis for east west direction, okay, and for north south direction. So in that case we have 13.9 feet kip moment, and similarly if you use the same equation, so you got 7.6 feet kips. See here I use the equation, that's the shortcut one, okay. You say you get the same value, like you see here, okay. This equation and this one are same, okay, because the geometry is same, and similarly here you can also use this equation, okay. You will get the same answer. Now remember this is very important, that how to represent this movement. Let me discuss it, okay. Let's say this is my okay, let me show. So remember that this is my north south direction, okay, this is my north, this is my south, and this is my east, okay, and this is my west direction. Let's say I pick this column, so you see here that in the long direction or in the east west direction, or let's say this is frame A, for frame A, which is the sorry, this one I choose this column, okay, because we run the analysis for the interior frame, not for the exterior frame. So you see here we got a moment right here, which is 9.5. okay, so here we got 9.5. okay, 9.5. And similarly this is in longer direction. When we run the analysis in the north-south direction, in the short direction, so this moment is basically, you see here, for by this line. okay, let's say this is my x. okay, and similarly this is my y. So now this moment is about what x is. This moment is about the z axis. okay, it should be remembered in the plane. But if you represent this situation, let's say in 3D, okay, let's say in this direction. Now let's say this is my z direction, the height is my along z direction, and this is my y axis, and this is my x axis. Now you see this movement is about the y axis. Clear? This movement is about the y axis. So now this movement is about the y axis. Clear? Which is 9.5 kf feet. Now the next movement, which is in this direction, and that movement will be about the x axis. Remember, because we are now running the analysis in the y direction, or in the north south direction, and we got the moment is, that moment will be about the x axis, and that moment is, we got it here, that is for the interior column, this is 7.5. so that moment is 7.5, 7.6, sorry, 7.6. now you see this is my MUX moment. okay, this is my MUX, and this moment is my MUY. okay, but this is only due to live load, or you can say vertical gravity loading. Now you have to run the analysis if there is wind load, earthquake load. Once you got the movement for earthquake load, wind load, we have to add those movement with these movements, algebraic sum, and then finally you got the net moment. So this is MUY, this is MUX. MUX is about the x axis, MUY is about the y axis. Let's say we assume we have no lateral loading, so then we will find the shear, the vertical shear, which can be easily determined, okay, by just finding the tributary area and multiply it with Q. You got the vertical shear. So you got your VU, your PU, MUY, MUX, and then go for the design of biaxial column, as I already discussed it in lecture number 7. okay, so this is the procedure how to calculate the moments. Clear? Now next we have an investigation of shear by moment transfer. okay, this is very important, and we will do this example, okay, after completing the rest of the portion of this lecture, because this moment you couldn't understand this procedure until we understand the theoretical portion of the shear, which is transferred by the unbalanced moment. okay, so see you in next lecture, which is very important lecture. okay, finally you see how we basically accumulate those moments, how we deal with these moments, these unbalanced moments, and how these unbalanced moments cause, you can say, eccentric shear. Remember, this is very important. When you have an unbalanced moment, due to this unbalanced moment, the shear which is caused is not acting over the centroid of the column, it is acting somewhere else. okay, and we assume that shear is basically, because it is not fully mentioned in ACI code, so we assume that we already determined the the critical shear parameter. So in that case, let's say if this is an H column, so we will find the centroid of that shear parameter, and at that point we basically assume that the shear which is caused by this unbalanced moment is acting over that centroid. So how to calculate the centroidal axis, how to calculate that unbalanced shear, or you can say eccentric shear, and how that eccentric shear causes the movement, further movement about the centroid of the column. So you will learn this inshallah in the next lecture. Thank you for watching. See you in next lecture.